The next topic is constitutive relationships, which define the relationship between E and D. It also defines the relationship between B and H. So if you know the relationship between E and D, and you know the relationship between B and H, then you can say that you know the constitutive relationships of the material. Okay, so we start with a very simple material, free space. We all know that in free space, the displacement field D can be written as D equals to epsilon sub 0 E. Besides, the B field can be expressed as B is mu sub 0 H. Here, the epsilon sub 0 means the permittivity of the vacuum. And mu sub 0 is the permeability. Of vacuum. I believe that you all are very familiar with these two constants, so you should know the values of these two constants. We learn that epsilon 0 is the inverse of 36 pi times 10 to the power of minus 9. Besides, you can write it as 8.854 times 10 to the power of minus 12. The value of mu sub 0 is 4 pi times 10 to the power of minus 7. Okay? From these two from these two constants, you can derive the speed of the light in vacuum. The speed of light in vacuum is c, which is the inverse of the square root of epsilon 0 and mu 0. And take these two values into this expression. C will be appropriately equal to 3 times 10 to the power of 8. Okay? Besides, we can also find out the intrinsic impedance of vacuum. The intrinsic impedance here means the in Mandarin you can write it as this. And we know that the intrinsic impedance is defined as eta 0 equals to the square root of mu 0 over epsilon 0. And take the values into this equation, you can know that eta 0 is approximately equal to 120 pi, or you can say that it is almost 377. This is the intrinsic impedance of the vacuum. And these two is the constitutive relationships of free space. Okay, before we figure out the constitutive relationships of a dielectric, we shall learn the polarization of materials. As we know, consider an atom. Here, you will have a bound positive charge, and a bound negative charge. These two charges are separated by a distance. As a result, we will form a electric dipole. For a dielectric, there are a lot of atoms inside a dielectric, and each electric dipoles they point to randomized direction. As a result, you cannot feel the net effect of these electric dipoles. However, if you applied the external electric field like this, all these electric dipoles will point to the same direction by this external electric field. Therefore, we can feel the net effect of these electric dipoles to form so-called electric polarization. Here, the electric polarization P should be in proportional to the external electric field E. As a result, we can write P in terms of epsilon 0 times chi E times E, where this term is the electric susceptibility. Okay, and I believe that you have learned that if you know the P vector, then the D field can be written as epsilon 0 E plus P. Okay. Similarly, inside an atom, we have positive nuclear, but we have negative charges around the nuclear, so we will form magnetic dipoles. And initially, each magnetic dipole they point to different direction. As a result, you cannot observe the effect of all these magnetic dipoles. However, if you apply the external H field, this H field will point these magnetic dipoles to the same direction. This external H field will make this magnetic dipole to point to the same direction, so they will form the M vector, which is so-called magnetic polarization. Again, the magnetic polarization M should be in proportional to H, so we write it as M equals to chi M times H. This term, chi M, is magnetic susceptibility. Okay, and after finding out the M, the B field can then be expressed as mu0 times h plus m. So these two define the relationship between D and the E and the B and the H in the dielectric. So these two are the constitutive relationship of a dielectric. Now, let us rewrite the general characteristics of the material. In previous slide, we have learned that the D field can be written in terms of the E and the P, like epsilon 0 E plus P. Okay? Besides, the P should be in proportion to E. So we put this expression into the equation and we can rewrite it as epsilon 0 times 1 minus chi E times E. Okay? And this term can be rewrite as epsilon R, or we can combine these two to be just epsilon here. So in this expression, the epsilon means the permittivity of this material. And the epsilon R here, clearly, it is the ratio between epsilon and the epsilon 0. So epsilon R is defined as epsilon over epsilon 0. Generally, the epsilon of material should be larger than epsilon 0. So epsilon R is larger or equal to 1. And epsilon R is so-called relative permittivity, because it is the ratio between epsilon and epsilon 0, so we call it relative permittivity. In some papers, you can also see the epsilon R is defined as dielectric constant. These two items means the same thing, that is epsilon R. Besides, if you are from the area of optics, you should learn that epsilon R is also equal to the square of n, where n means that the refractive index. So n can be written as equal to square root of epsilon R. So if you know the dielectric constant of a material, you can just use the square root of the dielectric constant to find out the corresponding index of this material. Okay? Besides, we know that the B field is mu 0 times h plus m. And here, m is chi m times h. As a result, we can rewrite B field in terms of h like mu 0 1 plus chi m h. And this term can be written as mu r. Okay? And these two can be combined as just mu here. So mu is so-called permeability of the dielectric. And again, mu r here is the ratio between mu and mu 0. Which is so-called relative permeability. Usually, for non-magnetic material, mu r is 1, but if you consider magnetic material, mu r will not be equal to 1. But in the following part or in your common research, we only consider non-magnetic materials. As a result, without any assumption, you can just take mu r as 1 in your research or in your consideration. So, these two are the general characteristics of material, and you can say that these two equations are the general constitutive relationship of material.